camera's microphone was placed at 100 centimeters, which was directly in between the two speakers, and what you just experienced was destructive sound interference. When I began to move one speaker towards the microphone of the camera, you realize at one point it gets quieter, and then after that point it begins to get louder again. And when I begin to move it back away from the microphone, you realize that the same thing happens. It gets quieter and then louder. And this happens to happen at about 32 centimeters. The reason why we didn't experience complete destructive interference was because there's sound bouncing off the walls of the room, and it is difficult to get precisely half a distance of a wavelength from the microphone. Both speakers were giving off an output of 531 Hertz, and the equation for frequency is velocity over wavelength. The velocity of sound in air is known to be approximately 343 meters per second. So from this, we can calculate the wavelength of a wave with a frequency of 531. So lambda equals velocity over frequency, which is 343 meters per second over 531 Hertz, which is approximately 0.63 meters or 63 centimeters. Phi equals delta L over lambda times 2 pi is the equation for phase shift. The destructive interference happens at phi equals 2m plus 1 pi, where m is integers 0, 1, 2, 3, and so on. Using this equation, we can solve for delta L over lambda for destructive interference to be 0.5, 1.5, 2.5, and so on. So since destructive interference happens at half wavelength intervals, we can now explain why we experience destructive interference at around 32 centimeters for a sound wave that has a wavelength of 63 centimeters.